The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, first, looks like a lot of people is outside today, nice weather. Midterm number 1, we will have it the week after, Wednesday after you come back, and that on April 4th. And as the email Jonathan sent out before, you will be closed book, but you will allow one sheet as much as you can cram into it. Right. Okay. So one sheet notes, and I'm asking Jonathan to put the previous example of the midterm online, so you can use that as an example and expect the similar level. And I will cover the first 5 chapters. So actually, essentially by Monday, I'll finish chapter 5. And so we do have a homework, number 6, also due on that same day. Because they say you need to do homework to get familiar with the content of chapter 5. Any questions? Okay. Don't worry, the purpose is not to test you. It's just a chance to, the second midterm is open book, it's take home. So this is the first chapters in a sense is some of you came to me and say, can pass the course. I can't guarantee you pass course, but say, I think if you really know the content of the first 5 chapters, you should be able to answer a lot of questions on the micro nano core qualifying exams. The micro nano core is in the form of giving you a paper to read, and they come back answer questions from different angles. So that's my feeling is you should be able. Okay. So coming back to the last lecture, we discussed what's the energy carried by electromagnetic wave, that's a Poynting vector. And then we took the plane wave solution of electromagnetic wave in a medium, and we calculated the Poynting vector. And from that, we learned that the energy, the Poynting vector, decays exponentially, say as determined by the absorption coefficient, which is 4 pi kappa over lambda. I recall for optical waves, lambda is 10 to the minus 5th, right? So essentially, kappa could be a very small number, 10 to the minus 7, and it's still very important because you do 4 pi, and say 10 to the minus 7 divided by 10 to the minus 6, you get a 1. And that means it's still 1, okay, depends on the length, of course, is exponential alpha x, right? So this x is when delta is inverse, say x equals delta, that equals inverse of the alpha, this exponential is really 1. So that delta is the penetration depth, as I say, when the light intensity decays exponential minus 1. So that's the EM wave propagation inside the medium. That's a Beer-Snell, we said. And then we started looking at the reflection and refraction of EM wave at the interface. And for that, we have to be careful of the polarization, right? Say for electric field, if it's pointing in any direction, we can decompose it into a TM wave and a TE wave. And the plane of incidence defined based on the wave vector of the incident as the norm, right? So if the TM is transverse magnetic, that's an electric field that is in the plane, That's why it's parallel. This P means parallel, and symbol parallel. And TE is a transverse electric wave. That's the electric field is perpendicular to the plane of incident, perpendicular. And S is probably German for the perpendicular, if anybody knows German. Then we have, based on the boundary condition derived from Maxwell equation, we can eventually write down what's the reflection coefficient. That's not reflectance, because it's the ratio of the reflected electric field. This is the field ratio, reflection coefficient and transmission coefficient. So I'm not going to repeat those formula, but essentially you can calculate the reflectance based on reflection coefficient and transmission coefficient. You can calculate reflectance and transmittance for any angle of incident, and as long as you know the refractive index of both sides of the medium. And this is, of course, assuming perfect interface. Remember, we have not I made a comment of this wave vector conservation, right? So this is a specular reflection, and that's what the Snell law tells us. The angle of incidence equals angle of reflection. And but see, I like to always, if you want to show your knowledge, right, and very useful. This is always I say for my student, I say a skill that you should develop over the graduate years. If you haven't developed over undergraduate years, is when you walk out, you solve over 90% of the problem in 5 minutes. That's I say it's a back of envelope skill, because so somebody give me material, I say, okay, that's the refractive index range, and that's what I know roughly what's the reflection, right? So this is a perpendicular incidence, right, formula, and that's you don't need to remember the angular dependent, but this is the one that I keep in my mind when I do my back of envelope given any surface, right? And so we use a glass and silicon as an example. So you can see the typical reflectance of those materials. And I stop there. I want to do more discussion. One, we say, if we look at the Snell law, the incidence, the wave vector conservation, right? So we got N1 sine theta 1, theta I, that's the angle of incidence, equals to N2 sine theta t. This is the transmitted, right? So we have, this is the light comes in, and typically air, which is a vacuum, for pretty much a vacuum, depends on the wavelength. And the refractive index is 1, and then inside the material, typical refractive index is larger than 1. And so your angle is bending, the refractive angle theta t becomes smaller, right? So this is Snell law. But you could have an opposite case where the light is traveling inside the medium and go out, right? And after it goes to the first surface, it may go, say, inside the medium. And so in that case, if N1, so if N1 is larger than N2, right? And you can say my say refracted angle theta t is larger than theta I, right? So this is my theta t is larger than theta I, and then eventually you come to the situation where the theta t goes 90 degrees. So you ask what happens after that, right? So if theta t equals 90 degrees, you get a sine theta I, and we say this is a critical angle equals to N2 over N1, and you can say this ratio is less than 1. So at this angle, above this angle, where theta I is larger than theta I critical, and you go to check the say reflectance and transmittance formula, and you find that R equals 1. So the light is totally reflected. Reflectance is 100%. So R equals 1, and that's a total reflection, or total, sometimes is a total internal reflection, right? So this is internal means, for example, if you go from inside the glass into air, right? The light is confined in the glass. And so it's interesting. You can put in the typical number. If this is air, it's going from glass to air, right? Air is 1, glass is 1.5. So 1 divided 1.5 oxide. I think in that case I got 42 degrees. So that's actually a very large angle, right? If you have glass, and what it means, if this is 42, so any light with the incident angle larger than 42 degrees will not escape the glass. Okay? So this is the principle of optical fibers, right? So optical fiber has an inner core, and then say has an outer core, and this outer core has a smaller refractive index. So during the glass deposition, pulling, they change the composition of the outer layer to make the outer layer smaller refractive index, so that when your light comes in, it will keep bending and inside. Okay. So when you use the optical fiber, you don't want to bend it really sharp, because that angle of incidence will be above the critical angle, the light will leak out, right? And in fact, yesterday I was in Baltimore having lunch with somebody who was, he said that he talked to, this optical fiber, say was awarded Nobel Prize a few years back, right? So it's a very simple idea. And he said because I was having lunch with somebody from Corning, so we're talking glass, and this guy was saying that he asked the Corning inventor about the idea at the time. He was proposing using this for the communication application, right? And how people reacted. And people were just saying, that's crazy, right? You're thinking about glass, because before that, everybody used the communication as electrical wires, right? Going from electrical wire, to glass, you can say some of the even very simple idea actually gets very hard to be accepted. This internal reflection is really simple physics-wise, right? And but there are a lot of lead ideas and a lot of application. If you're an engineer, the simpler is better. And then I can share a few, right? Say if you think about, I said glass is 1.5. If you do silicon, silicon is 3.5. 1 over 3.5 oxide give you 16. I have 16.6 degrees. So which means, right, silicon, all the light above 16 degrees coming to the surface doesn't go out, right? So this is where people use this idea to do light trapping in silicon, right? We said silicon is an indirect gap semiconductor. It's not good at absorption. And so if you think about this, okay, I have surface here. I got a roughness coming in. The light comes in here, but the reflected over angle into here. And the other surface is, if it's totally internally reflected, it will come back, right? So you have traversed a longer distance and bounce more times, and that's how you can reduce the thickness and yet still achieve higher absorption, right? Light trap. And this is still a very active field of research. This is a geometric optics. We're just talking about trajectory of light, didn't consider the phase. But how to actually achieve maximum light trapping with the smallest material is we have, for example, a DOE project trying to make thinnest solar cell, but they still have silicon-based, but still achieve high efficiency. And let me give another, there are many, many examples using this. I remember at the peaks of the, say, optics, say, the photonics. If you're, say, probably around 10 years ago, there was a big bubble, like a Hausen bubble, not as large. But say the stock went the very roof. A lot of optics communication company got very rich, right? And because that's the internet, and after that is the internet. So one of the challenges is how you switch light directions, right? And there was this lead idea doing MEMS switching, micro switching, right? So this idea was say basically you have a channel, right? And you have light comes in, it's typically totally internally reflected, so it doesn't go through. And then next time you push a liquid that has the same refractive index as a glass or very close, right? In that case, you have say index matched and doesn't have a total internal reflection anymore, so it just goes through, right? It's a very simple idea. And I think that was from HP. I don't think they were successful commercializing it, but those are the. And in fact, all the lasers use this effect. So not all, but most lasers. So the solid-state laser, what it has is a quantum well, very thin gallium arsenide, right? And this is a quantum well is where electrons and holes recombine and give off a photon, right? And that thickness of that well is about 100 angstrom or thinner, but the light wavelength is much larger, right? So what it has is there is another cladding optical layer. So this is the charge, and the electromagnetic wave goes this way, and the refractive index of the surrounding layer is smaller, so the light is forced to bounce along the layer direction. So this effect is widely used in many, many devices. Very simple, and it's a total internal reflection. Okay. But there is even something more interesting, and that is you can say that when theta I is larger than theta, say about critical angle, the reflectance is 1, but the T, right, the transmission coefficient is not 0. And in fact, you can go to check the transmission coefficient for we derived is 2n1 cosine theta I and n2 cosine theta I plus n1 cosine theta t. Okay. Cosine theta t, I didn't say mathematically, I didn't say it's 0, right? Because we have, if theta I is larger than critical angle of incidence, that means I can still use Snell law, sine theta I. Mathematically, that's a solution of Maxwell equation. Maxwell equation didn't exclude it, right? So theta I, if you go to do this, you'll see is larger than 1, sine theta I, right? And sine theta t, the angle of transmitted, right? It's imaginary. You go sine, that's an imaginary number. And cosine theta t equals 1 minus sine theta t squared. And this is larger than 1, so this is the imaginary number, right? So let's say it's I times B. So I substitute this one back into the transmission coefficient. It's not 0. right? And I look at the field on the other side. So if you look at the transmitted field, of course, it is proportional to transmission coefficient, and the incident field, I have maybe the angle is not quite right, so let me write it just into proportional. And then I have my exponential factor, the phase factor, minus I omega t minus n2x sine theta t plus n2z cosine theta t over C0. So that's this is not 0, this is the incident, right? My electric field on the other side is not 0. Okay. And what happens is cosine theta t is imaginary. When cosine theta t is imaginary, I have an imaginary number here, I have another imaginary number here. It gives me a real number, right? And that real number is exponentially decay. So my electric field on the other side is exponential decay function. And this is the Evanescent wave. So when my angle n1 is n2 and angle of incidence is larger than critical angle, right? The electric field on the other side exponential decay from the surface. And the real part, the x component, if you look at n2 sine theta t equals n1 sine theta I, so that's actually real, right? So this wave, what you have is a wave propagating in the x direction on the surface, and decays exponentially on the other side, right? And this is the Evanescent wave. Okay, and but you see, how is that possible? You have a field, the transmission is 0, right? So what happens is you go to calculate, although the t itself is not 0, but the tau, the transmitted energy is 0. The average pointing vector is 0. So the field comes in, goes out, back. So the average speaking, there's no net energy go from one side to the other. That's what the Evanescent wave. And recall, in the case of discussing electrons, that's our situation, right? We say, okay, your energy of the electron comes in, goes. Say if the energy is less than the barrier height, your wave function on this side is not 0. Right? But you got calculated the material flux, the particle flux is 0 on the other side. That's the Evanescent field for mature wave. So all waves have these characteristics. Okay? And how fast it decay, you go to check. Here is essentially, if you say omega over t, C0, and the theta divided is of the order of wavelengths. So that decay is of the order of wavelengths. And then we said that, okay, for material wave, the wavelengths maybe is a few angstroms. Right? Last time we say people use that to do the IBM interview example I told you. Finish, get the scanning tunnel microscope. Let's use the Evanescent wave for material wave, electrons. Here, you got the Evanescent wave on the other side, and there are a lot of, say, different applications I'll discuss more later on. Okay? So this is the Snell law and the Evanescent wave. And let me also make one more comment, because here all our derivation is assuming N1, N2 say are real, and if N2 is complex, okay, and you go to check your equation, derivation process, no problem. Everything still is applicable. It's mathematically a solution of the Maxwell equation. So what it means is when you look at your Snell law, n1 sine theta 1 I, let me assume n1 is real first, okay? And you get say n2 is complex, so sine theta t is complex now, right? So sine theta t is complex, is a plus bi, and cosine theta t, you do your operation c plus di. So both are complex. And it's the same formula, you do your complex number operation. Okay? But when both are complex, you go to look at your wave here, right? Sine theta t is complex. Cosine theta t, okay, in fact, here will be real. But say, what you find out is that this wave, inside, when it propagates into a medium, the constant amplitude is actually, in the z direction, is a constant amplitude surface. Right? The amplitude, that's when z, each z equal constant, that field is a constant amplitude. But constant phase is going in the other direction. So the constant phase, constant amplitude actually do not coincide, and this is an inhomogeneous wave. But say all the formula we gave still applicable. So there's no problem as long as you do your complex number operation consistently. And I remember, say, in those days I only know Fortran, so you have to be very careful, declare your complex numbers, otherwise you run into problems. One more. What about N1 is also complex, right? N1 is also complex. And this is a point that probably most people don't know. Everything is still applicable, so most people know that. Okay? But if you do your operation, you find that r plus tau do not equal to 1. Okay? And at the surface, there's absorption. So I remember I found this out when I was a graduate student doing all the maths, and said, what's happening there? So I went to go, I went to ask my professor. He said, that's strange. Okay, so I went to check a lot of books. I saw that I could write a paper. It turns out I was only 100 years late. Okay, right? It was in Max Born, in fact, that they discussed all those issues. Right? Max Born is a say, they Born got the I forgot whether he got a Nobel Prize or not. But say it's all in there. Say discussed before. Okay, so this is all the discussion that I didn't finish. And so we now know at least say how to calculate the reflection of electron at the interface. We gave a normal incidence. I said that you should be able to do any angle. We did say electromagnetic wave at the interface. And the next one is acoustic wave, right? So all those waves are similar, but the equations are different. One is the Schrodinger equation, here is the Maxwell equation. So let me briefly talk about acoustic wave. This is my last, because I go from simpler to more complicated. Mature wave, in fact, the Schrodinger equation there is a scalar, right? Maxwell equation is a transverse wave, 2 component. And you learn the full-length acoustic wave are 3 components, longitudinal wave, 2 transverse waves. So your equation will be a lot more complex. And in the continuum limit, right? In continuum limit, you can write a set of differential equation for acoustic wave propagation in the medium. And the way to derive that equation is, say, starting from F equal ma. Right? There are not many equations. And so the F equal ma, and then we need to say inside the material how I can convert this into the atomic displacement. Because acoustic wave is essentially the atoms, the material displacement from equilibrium position. Right? So if you say, okay, displacement is the r minus r0, that's the equilibrium position, then A is just the derivative, right? Second order derivative. So now you can try to say how you can relate both sides so that you get the one equation, right? One equation for displacement or velocity of the material wave. And the way you do it is think about the force is related to stress in the material, right? And stress is related to strain. Strain is related to displacement. So if you write all those relations, you immediately get a wave equation for the displacement. And that's the acoustic wave equation. Okay, just a few more on that. And what you have here is the strain. Typical way of writing strain. I'm not going to write all the equation. So strain is, say, a tensor, and is defined as dui dxj plus duj dxi. Okay, and that's the strain. And stress tensor. Okay, so we have what's the Hooke's law in the material. In the complicated form, the most say general form is really a tensor, right? Say the force, the stress is related to the strain, right? Is related to the strain S. So this 2 hat means a second order tensor. Okay, and that coefficient, right, is the stiffness, material stiffness, elastic stiffness constant, and this one is something times tensor. I say is actually to get a second order tensor from a second order tensor multiplication. This should be a fourth order tensor. Okay, so this is really fourth order tensor, and each order is a 3-component vector, is 3-component. Second order tensor 9 component. Fourth order tensor is 81 component. Okay, so anybody do solid mechanics, you must be very good in the math. Okay, that's a lot of, say it's a tensor operation. And in the case of, in fact, you can, due to symmetry, you can simplify 81 to 36. And if you get an isotropic material, you get only 2. So that's the different assumptions made. But essentially, so you have displacement, you have your stress, and your force, right? Generally, if you have a surface, you have a norm, you have stress tensor here, sigma, right? You have n is norm. Then they say is the stress tensor, say the norm times a stress tensor. That gives you the force acting on that surface, right? So essentially, here those relations give me, if I substitute everything back into the F equal ma, I should get acoustic wave equation in the material. But say, except here, if I was to look at this, I know this one, I get the time or second order time derivative, right? On the left-hand side, I should get the space second order derivative to get a wave equation, right? So the way I just wrote the F equals n sigma will give a sigma equals, say, proportional to S. That's only first order in space. It's not second order in space yet. And the reason is you have to do your finite element analysis. So you take a differential volume, right? You have force difference, right? That's the net force. That difference will give you the space second order derivative. And so you got the, say, second order derivative on the left-hand side, second order time derivative. In the right-hand side, you get the wave equation. That's acoustic wave equation. You can see if I write it down, it will be very, very long. Okay. So this is in general, you can have the equation for acoustic wave. And if you can also calculate, there is also acoustic Poynting vector. That's the energy. Okay, the time average the acoustic Poynting vector. This is not the strain Poynting vector is 1/2 real part of velocity, which is the first order derivative, and times the stress tensor. So this is like the force times the velocity gives you the work. That's the energy flux there. Okay, and now what happens for acoustic wave coming towards the interface? Okay, and when we have electromagnetic wave, we have, of course, reflection and refraction, and that's the same we have. But it depends on whether the incoming wave is a longitudinal wave, is a transverse wave, and if it's a transverse wave, which direction I project, right? The plane of incident. And so if the displacement is in the plane of incident, that's a SV wave. And here, longitudinal wave, this is an L wave, right? And in most general case, what happens is you do your, again, at the interface, you have boundary condition, and you can derive. And it turns out, in general case, a SV wave or a longitudinal wave can excite 3 waves. You can have also longitudinal wave. You can have SV wave and SH. SH is the other polarization perpendicular to the plane incidence. So that's the complication for acoustic waves. And you have mode conversion. Okay, from one mode, one polarization to other polarization. And if because of this, you can also have transmitted also have 3 polarizations. Okay. And if it's an isotropic medium, you only have 2 branch, right? So this will be degenerate, and you can have L waves and say the transverse wave. So this is the general case, and the formula. In fact, there was a really good book when that's a book by O. I would suggest if anybody interested in those, because it actually treats Maxwell equation and the acoustic wave equations side by side. And that gives, say, very good learning. And then when I read acoustic waves, so that's I know Maxwell equation. That's how I learned acoustic wave. Okay. And now, if you go to do, I'm not going to give you any angular relation, but the reflectance of acoustic wave, right? At the lower incidence, is very similar to the reflectance of optical wave at lower incidence, and same as the electron waves at lower incidence. So reflectance is Z1 minus Z2 and Z1 plus Z2 squared. Well, this is Z is density times velocity square root. And this is acoustic impedance. Okay, so it's a density times velocity, speed of sound. You can roughly think that, and again, it's the difference in acoustical impedance that gives the reflection of acoustic waves, right? And you can write the Snell law, and for example, the problem is for Snell law, this is a vi angle, say velocity of the incident wave, but say even on the same side, you can have reflection to other angle due to mode conversion, right? The lateral momentum, so kx has to conserve. That's a Snell law. And so what you have is even for the same side, right? Let's say reflected also for longitudinal, let's say. Then you have to say the longitudinal wave, there's the angle there, angular relation. That essentially tells you the lateral momentum conservation. And for the other side, you have similar, right? If it's transmitted, way t transmitted, say on the, say let's say reflected side, transmitted side. So those are the corresponding Snell laws for acoustic waves. So again, you can have if you look at those relations, you can still have total internal reflection. Right? Acoustic wave can also be totally internal reflected. So if you go from medium, like say, I think it's germanium, for example, to silicon, if you launch, say, lattice waves, and you look at the relation, there is a critical angle, and above the critical angle, there reflect total internal reflection. And on the other side, then you have correspondingly an evanescent wave. Doesn't carry energy to the other side, but atomically there is vibration, exponential decay from the surface. Okay, so all those waves have similar phenomena. You see the equations you start with could be very different, but general wave behavior share a lot of similarities. Okay, so that's waves at a single interface, right? And what we're moving on there is, what about multiple interfaces? And single interface is only reflection, refraction. I do want to, before I read this, I do want to make another comment. We said that, okay, because this is Snell law, right? If n is negative, you draw your light, how the refraction should happen. Then if n is negative, it goes this way. Your theta goes the other way. So that's why at the beginning there are a lot of news articles of light bent the wrong way, all this stuff on electromagnetic metamaterials. Okay, so what we're approaching next is multilayers, thin films. In thin films. So when I say that before we have one interface, now let's go to two interface, right? That's so go from two interface to n interface is actually quite straightforward. And so the physics, what happens is I have the wave comes in. The first interface, let's say N1, N2, N3. My formula is written in terms of a small n, but you can write a capital N. Everything is identical. Okay, and so what happens is at the first interface you have refraction, you have reflection. You can use your Snell formula to calculate that reflection and refraction transmitted. And when it comes to the second propagate, right? We know how to write the wave propagation, the phase factor here. We have the phase factor, right? That's my phase factor. So when the Z change, I know how to write it down for different media. And then at the second interface, you have reflection, you have transmission. And once it's transmitted in N3, I don't have anything coming back, so I can say that part is going forward. This one coming back is troublesome because it come back and hit the interface again. And then I get, again, transmission from 2 to 1 and reflection. Every time I can use my Fresnel formula plus the propagating phase factor to trace, right? So transmission, reflection, and that's one way to do it. You add up the field, you use the Fresnel formula, but it's pretty tedious. You can say it's an infinite series because there are infinite number of reflection, transmission in theory, right? So that's you trace the field, and if you don't consider the phase of the light, right, EM wave, then that's people do. This is pretty much like a Monte Carlo. People do retracing. They trace the trajectory of light bundles, and there are commercial code to do that in complicated geometry. But when you have those phase also changing, it becomes a lot more complicated to actually trace and carry your phase of the field, and not very computationally efficient. So at least for thin films, flat structure, there are different other ways to do it. And the next way is here at each interface, I can use the Fresnel, right, formula. But say the next one is I don't care about the I add this all together because the phase factor is the same for each one, right? So okay, I say this is my incident. This is a total resulted reflection, right? And this is my total forward propagating and my reflected propagating inside the film. And this is my total transmitted, right? And in that case, I do not know the relation between this point and this point because this one is summing up many of those forward. Same, this is summing up many backward, right? So I have to use my boundary condition to refine the relations among the incident, reflected, here is forward, backward, transmitted. So this is another way to do it using boundary condition, right? And this is a resultant wave. Let's say positive. This is a backward propagated, reflected, and incident. And of course, there are different polarization. If I consider TM wave, then that's what I have to do as we do a single plan. And here is transmitted, right? So that's a way that I'm going to follow through some math. And even this way is pretty intuitive mathematically. But even this way is not very convenient if you have many layers. And if you have many layers, the best is using a matrix format. Okay? And the matrix format is not, say, I consider total electric field. This is incident reflected, right? But I don't distinguish incident reflected, the total local electric field, and the total magnetic field. So here I have, and the point I want to use is the continuity, right? If you record a boundary condition for EM wave, is that at the interface, I have the tangential component of electric field, the magnetic field, as long as there's no sheet current there, is equal on both sides. So so what I'm going to do is say I use I know the phase factor from this point to this point and from this point to this point. So I know actually the relation, the relation between the electric and the magnetic field between these 2 points. And these 2 points will be reflected as, let's say I have EX0, HY0, that's at this point, relate to this point through a matrix. And that matrix you can get from the solution of Maxwell equation. And then to this point is EX, let's say here I have D, this is thickness, and HYD. So this matrix will make my life much easier, because if I know so you relate the electric field total, it's not forward, backward, it's add up or forward and backward, total electric field, total magnetic field at this point, through the total electric field, total magnetic field through a matrix element. And then now my continuity, say, propagating to the other side, this electric field and magnetic field is the same on both sides. So this point is the same as this point. So I can connect many, many layers together just by matrix, say, multiplications. Continue this to build up any layer. So this one is most convenient to use, and that's transfer matrix. And in fact, the transfer matrix is used widely for many different problems. There are people dealing with multi-layer heat conduction, right? And in that case, your continuity is the temperature and heat flux at the interface are continuous. So using that, if you can relate the temperature and heat flux at this point to this point, and across the interface continuous, so you just say write a similar matrix, and you do your matrix multiplication for many layers, right? So it's a very useful mathematical approach for many different problems. But say what I'm going to do is spend a little time here, and let's use this to get the basic idea how I'm going to do multi-layers. And what we need to write down is essentially like a 2 interface condition. Before last lecture, we wrote 1 interface, we had 2 equations. And now I have 2 interface. And I need to write the propagating, the phase I need to carry, because from this point to this point, there's a distance traveled. And if I look at this, right, plane wave, when go z is moving, right? Omega is the same. And the x component, that's they say is the Snell will take care. So this one I don't need to vary. All Snell law is always valid. And omega t I don't need to vary. What I need to vary is carrying this phase term, the z term, because I go from, this is my z direction, right? When I go from this point to this point, I have, if this is the origin 0 to d, that's my z. Okay? So what I have, you can write your EI, the incident, and the exponential mass I, the phase factor. I write z directions n2, no, say n1, n1 cosine theta I, and lambda z. So this is my incident, and similarly reflected. So you have to be comfortable in carrying this positive n1 cosine theta I because of Snell law, so theta, the angle is the same, z, right? So this is the incident reflected in medium 1. And same, you can write the transmitted, right? The forward propagating E plus. Like I said, I do not. This is not just this. The origin is not just from EI. It's from the multiple reflection. So I don't know the relation. So I want to say this is the E. Let's say plus exponential phase factor inside is I n2 cosine theta. Let's say here I'm using 2 and lambda z. And E minus exponential, that is the opposite direction n2 cosine theta 2 lambda z. Right? You can also write the transmission there. Now I apply the continuity, the same boundary condition as I did before for the first interface and for the second interface. The tangential component of the electric and the magnetic field are continuous, right? So for the first interface, when I take my origin of z equals 0, cleverly choosing your coordinate, okay? So that is the tangential component, so EI times cosine theta I plus ER cosine theta R equals E plus cosine theta 2 plus E minus cosine theta 2. Right? So that's the tangential component on the two sides, this side and this side. Remember, I always add up total. I didn't say it's the incident or it's the total electric field. Yes? Yeah, I'm sorry. So this one is the same. Theta I, theta R is the same. Theta I. So the Snell law, right? And then say the magnetic field is N. Remember, say is N1 mu say 0 and EI minus ER, right? That's the relation we say HY we derived last time. The relation, if I know electric field, I know the magnetic field is N mu C times the electric field. For opposite propagating, because of the direction change, my right-hand rule, I have a negative sign in the front. Right? And the same is N2 mu C0 E plus and minus E minus. So this is the amplitude, E plus E minus, of the forward propagating and backward propagating waves. And of course, I need two other equations because I have E plus E minus unknown, ER unknown, and also transmitted unknown. I need two more equations to close this. That's at the other interface. I have two interfaces. Each interface give me two equations. Right? So the other interface, now you have to carry your phase factor. Because when the wave propagating from 0 to D, so you have to write Z equals D now. Again, your electric field is E plus here, right? Projected into the x direction. This is my x direction. It's cosine theta. So it's a cosine theta 2 exponential I phi minus I phi 2. Phi 2 is my phase factor. Let's say you can look at that as N2 cosine theta 2. So let me write it down. So phi 2 equals N2 cosine theta 2 over lambda times D. So E minus phi I phi 2 plus E minus and cosine theta 2 E I phi 2. This is a backward, going back. So the Z wave vector is going backward, so that's my plus wave, plus sign, right? And then say my ET transmitted, so ET cosine theta t exponential minus I phi 3, okay? And this phi 3 is, you do N3 cosine theta 3 lambda out times d. It doesn't matter. In fact, you can restart your coordinate this phase factor at the end, because when you calculate the transmitted, is this cancel all drops out, this phase factor, when you do the ratio. And so I have the magnetic field is N2 mu C0 E plus minus E minus. And this is N3 mu C0 and ET exponential minus I phi 3. Now I have 4 equations I can solve for the, what I want is really the reflected to incident, that's the reflectance, reflection coefficient, transmitted to incidence, that's the transmission coefficient, right? So I have enough equation to solve that problem. And what you find is your R equals ER over EI equals R12, that's the Fresnel coefficient between 1 and 2 interface, plus R23, that's the Fresnel coefficient, exponential 2I phi 2, and divided by 1 plus R12, R23, exponential 2I phi 2. So this is the reflection coefficient. And similarly, you can do your transmission coefficient. The ET EI equals T12, T23, exponential I phi 2, and 1 plus R12, R23, exponential 2I phi 2. So some comments here. So you can see the transmission, you have EI phi 2, that's the first pass, so it doesn't have double there, right? And the denominator reflecting that it's always double, so you have 2I phi 2, double the back and forth, right? If you look at this, the next transmission is reflection, come back, and go out. Reflection is the first one, and then the next one is have to go forward, reflect, go back, go out, right? So that's where this factor of 2 comes from. And second, you will see that if you square this, you'll get a sine, cosine, so you get the interference, periodic variations of reflectance and transmittance as a function of this phase factor. So that's the interference effect. Okay. And I do want to get the math down, so let me first give you the math and then do the discussion in the next lecture. So I have gone through the resultant wave method and really say split the electric field into forward and backward. But I said that if I do this, it's still not very convenient, and the best is to do this, transfer matrix. And using the fact that both electric and magnetic field are continuous at the interface. So what I need is to write, here I'm going to ask you to read more detail in the book. And if I want to get the transfer matrix, But eventually, I have also come back to what I care is the ratio. So, right, say I care about reflected electric field divided by incident. So I said what I do in math is the total. Total electric field is continuous. Total magnetic field is continuous. But at the end, I really want to still have to separate them for incident and reflection. So I need a matrix to relate that. And so if you do your balance, say your electric field, so this is at 0, right? This is my z, and this is my x. And let's say this is a 1, this is a 2, and so 1 x component 0 is EIX plus ERX. And H1Y at 0, so I'm considering a TM wave. So H1Y is N1 mu C0 and EI minus ER. You can see now I have a relation between incident reflected electric field to total incident electric field, total incident magnetic field, right? I can inverse this, and so or I write into matrix. So this one essentially because I want to write everything into matrix, H0, H1, 1, and here is 0, and this is 1 over P1 minus 1 over P1, and EIX, ERX. So I have this P1 is the surface impedance, so the EXHY. And for the TM wave, we have this cosine theta and N mu C0. So this is for TM wave. And TE wave, you can write a different expression, right? So what I wrote down here is the total electric field, total magnetic field relate to incident reflected electric field through matrix, right? So that's either the first side, because eventually I want to find the EI-ER relation, not just the H-E relation. But say what I'm using is E and H is continuous. So E and H, so E1x0, E1y0 should equal E2x0, H2y0. So that's the continuity of tangential component, right? So the second is my, if you go back to what we just written down on the electric field and relate to magnetic field, and you'll find out is E2x 0 and H2y 0. So I want to relate this point to this point. That's in the same media. That's just a phase factor, right? So if I do that relation, that gives me matrix. So this point is related to the other point. What I want is E2x at D, H2y at D. So this is this point here. Here, these 2 points, right? And in between is this matrix I want, and that's cosine phi 2 and minus I P2 sine phi 2 and minus I P2 sine phi 2 and cosine phi 2. So this is my M, transfer matrix. That's what I was saying here. Okay? And the beauty of this is I relate this point to this point. Now if I add another layer, layer 3, between here and here is continuous, right? So this point is also this point. Now to find this point, I time the other M here. If this is M1, this is M2. I time another M, I will relate to this point. Okay? So with the transfer matrix, this is my M. I say if I have n layers, it's just M1 times M2 times Mn. So I can do any layers easily. Okay? And finally is my transmitted, the last one, right? When it goes out, does not have anything coming back. So I still need to relate to that. So my final relation is, let's say if this is transmitted, EXD, HYD, so, and it equals 1 over P3 ETX, because in this case, this is my 1, 2, 3, and the transmitted field only has one forward propagation, not backward. So I have a simple, with this, if you can say, I can use all those relations. The first one, because this one is continuous equal to this one, so I have, you can say this matrix, 1, 1. Let me don't do this. I will use this one as my, this is my, here is my A. Let's say this is A. This is a matrix, right? So if I use my continuity as A times EIX HRX, that's here, that equals here. This equals this, that equals this. So equals M times this one, that's the other interface, that equals this. So 1 P3 and ETX. So with this, I can relate the transmitted to incident, reflected to incident. So this is the, no matter how many layers, I just add the multiplication of this matrix. Okay. And when you do, if you do this kind of calculation, this is people design any coatings. The design coating they'll do for as long as a thin film coating, you do your transfer matrix, and it has various kind of interference effects, and come into the desirable value. And when you do those kind of operation, the K is you have to be careful because sometimes this blow up. Okay, and depends on whether for example, if your phi itself is complex, that's actually exponential function. So this could create troubles. I think for this one, what I want to, I just want to stop here. Let me not showing the. I thought I was going to have some time to browse, but what I want to say is, if I have not lost you, first 5 chapters, you can now open any journal. You can make probably half of the paper connection to what you learn. And I challenge you to look at when I say in any journal, like don't consider the bioscience. Okay, I haven't talked about that, right? you will probably learn, I was looking at say nanolayers, energy environmental science, laser photonics, laser materials this morning. I think say I just don't have time to go through all this with you, but you should be able to say there's something that you can relate to. Okay? Any questions? Oh, today is beautiful. So I'll finish earlier.